This is James Evans, and in this lecturette, we're going to discuss long short-term memory, GRU cells, and the introduction of the idea of the memory cell into recurrent neural networks. While recurrence in neural networks facilitates the propagation of memory over time inside a neural network, nevertheless, that memory is transient, fragile, and potentially fickle, hence the introduction of the gated memory cell. As you recall, one of the great challenges in backpropagation on recurrent neural networks is backpropagation through time, which is sensitive to the partial derivative of the weights at stage I with the weights at stage I-1, leading to the problem of vanishing and exploding gradients, whereby the gradient exponentially approaches zero or infinity, bringing future sensitivities and learning in the network to a halt. The most prominent solution to this problem is gated activation. In gated activation, we explode the notion of the activation function to constitute an entire system or cell of gated activation. Here we gate the contribution of past to future hidden cells to increase the short-term memory. Enter the memory cell, which facilitates a kind of self-regulation of memory. And in its first instantiation in the long short-term memory cell, this memory cell lives independent of the pass-through activation and constitutes a regulatory mechanism by which inputs are turned into outputs, by which past sequence steps of the recurrent hidden layer influence current and ultimately future steps. We'll discuss two memory cells. The first and possibly most common is the long short-term memory cell, which includes three separate gates: a forget gate, an input gate, and an output gate, which sit alongside and regulate what enters the cell state, the memory cell state, and what goes from the state into the activation, which passes information to the next step of recurrence. As you recall, in a recurrent neural network, we have the hidden layer in the prior time step, ht-1, concatenated with x1, moving through a tan-H or a ReLU activation to produce the input to the next H. In the LSTM cell architecture, we add an entire memory cell atop that structure. ht-1, or the prior time step of the hidden state, concatenates with xi, the current input, and they trigger probabilistic switches. The first is a sigmoid that switches between 0 and 1 and can be interpreted as a probability to determine whether or not the cell state in the current period is going to forget or remember the cell state in the prior period or time step. The second probabilistic switch determines whether or not these new inputs should be added to the current cell state. If the sigmoid approaches 1, then it's multiplied by a tan-H activation, which normalizes the contribution of the current input and the prior hidden state into the current cell state. Finally, a third probabilistic switch, or sigmoid, is activated by the concatenated prior hidden state and current input to determine whether or not the current cell state will output its state into the hidden state moving into the next time step. The product of this probabilistic determination and a normalizing tan-H function brings information from the cell state into the next step of the hidden state. These three probabilistic switches, the forget gate, the input gate, and the output gate, allow the LSTM and the memory state which they manage to selectively retain information and convey information to the hidden states that will drive text or sequence generation. The gated recurrent unit, or GRU, is a simplified version of the LSTM and occurred much later. It involves only two sigmoid activations and combines the hidden state with the cell state. In a GRU, the prior time step of the hidden layer, or cell state, enters and is concatenated with the current data input, which could be the output of the prior time step if we're exclusively generating text or other sequential data. Those concatenated trigger two separate sigmoids. The first sigmoid activation, or probabilistic switch, triggered by the concatenated input and prior cell or hidden state is called the reset gate and is akin to the forget gate of the LSTM. Insofar as it approaches 1, the hidden state will remember its prior cell or hidden state. The second sigmoid activation triggered updates the cell state or hidden state with the information from the prior state concatenated with the input, normalized by tan-H. In this way, the update gate is akin to the input gate of the LSTM, and that's the end. The GRU passes all of its current state into the next time step of the GRU to be evaluated by the reset gate in that time step. How do you decide between the LSTM versus the GRU? Well, the LSTM requires more epochs to learn. It's also more expressive, it's more flexible, it's more sensitive because it retains an independent cell state. The GRU requires less training. It also produces less sensitivity and flexibility. One typically needs to add more GRU layers to get the same LSTM performance. And so if your analysis requires increased sensitivity, then it will be a toss-up, a flip of the coin as to which is more efficient, more GRU layers or fewer LSTM layers to achieve the best performance possible. As with simple, ungated recurrent neural networks, bidirectionality can improve the performance of LSTM and GRU recurrent neural networks for text generation, classification, and prediction.